Welcome back to another calculus video. I just watched my previous video and I don't think I sounded too awkward in it, so I mustered up the courage to make another one. So this one's going to be on surface integrals. First thing I want to talk about in this video is the fact that there are two different types of surface integrals as far as I'm concerned. So the first one is a flux integral. Basically it has a vector in it, and the other one's a scalar integral. So it doesn't have a vector in it. So to decide whether you should use the flux integral or the scalar integral, you just have to look at your vector function, or like the function that, or like your vector or scalar field. So if you're given a vector field to work with, then you have to use a flux integral. So for example, this problem that I'm going to go through in a moment, you're given a vector field because it has this arrow at the top of the f function, and it has an x, y, and z component. So you have to use a flux integral to solve this problem. Now the second problem that we're going to go over is going to require us to work with a scalar integral because there aren't any vectors here. There's no vectors. Or you could think of your scalar field as f of x and y and z equals 1. But then that wouldn't make it a vector function. It's a scalar function because it doesn't have an arrow, because like the f doesn't have an arrow on top, and it doesn't have an x, y, and z component. So I'm just gonna dive straight into the first example here. So we're just gonna evaluate a flux integral for this surface that I've drawn here. It's a cone. It has a bottom radius of 9 and a top radius of 0 because it's a cone. It doesn't have a top radius. So the vector field that we're going to be working with is x, x, y, z, and z. So the first thing that we're going to do is we're going to parameterize the surface so that we can find the normal vector. So it looks relatively circular, so we can substitute x as r cos theta and y as r sine theta. And that just makes z equal to 9 minus r squared cos squared theta plus r squared sine squared theta. And this just works out to be 9 minus r. So our surface becomes r cos theta, r sine theta, and r, or 9 minus r. So to find the normal to the surface, what we're going to have to do is we're going to have to take the partial derivative with respect to the first variable and cross it with the partial derivative with respect to the second variable. So in this case, the two variables we're working with are r and theta. So, okay, it's going to look kind of weird, but we're going to be finding the partial of r with respect to r. But just keep in mind that these are two different variables. So if we differentiate the x component with respect to r, all we get is cos theta. And the second component, or the y component, becomes sine theta, and the last component becomes negative 1. The 9 goes to 0, and the negative r just becomes negative 1. So that's our first partial. Our second partial, we're going to be working with the variable theta. So cos theta becomes negative sine theta. The r is just treated as a constant, by the way. R sine theta becomes r cos theta, and the last component there aren't any thetas in here, so we're just going to leave it as 0. So to find our normal vector, we have to cross these two partial derivatives. So if you all remember what a cross product is, the top row is just I hat, j hat, k hat, Second row is the first vector. So in this case, it would be cos theta, sine theta, -1. And in the last row, you're going to have negative sine theta, r cos theta, and 0. And it's all going to be inside a determinant. Now, because there's a 0 down here, I'm going to evaluate this determinant like this. Okay? That's just how I'm going to do it. You guys can do it a different way. There are different ways to do this, but because there's a 0 here, I'm just going to evaluate along this column. So k hat, the minor for k hat is cos theta, or just whatever's here. So that's gonna work out to be r. -1, minor would be there. Actually, I'll just do it like a normal person and go along the top row. So I hat is, the minor for I hat is going to be this. So it's going to be 0 minus -1 times r cos theta minus j hat. So 0 minus r sine theta plus k hat. Now, the product of these two minus the product of that two just works out to be r. You can do the math, but that you can just do the math, but I'm just going to tell you that it works out to be r. So then, if you evaluate this, you'll find out that your normal vector is r cos theta, r sine theta, r. Now the question is whether this is pointing outwards or whether it's pointing outwards of the surface or whether it's pointing inwards. Now, in the grand scheme of things, it doesn't matter, but in this case, we're going to aim to work with a normal vector that's pointing outwards. So if you want to figure out whether it's pointing outwards or inwards, you can try evaluating it at a certain point. So let's say we want to find the normal vector at a given point in the first quadrant. So if we want to do that, theta's got to be within 0 and pi over 2, and r is going to be, well, r could be any value. So let's say pi is equal to, or theta is equal to 45 degrees. No, it's not working degrees. Stay in radians. Let's say theta is equal to pi over 4, and r is equal to 3. So then this would make our normal vector 3 cosine pi over 4. I'm running out of space. That would make our normal vector 3 cosine pi over 4, 3 sine pi over 4, and 3. So these are all positive values. And by looking at our surface, if we have a normal vector that's in this quadrant that has a positive x, positive y, and positive z value, it should be sort of pointing into the page, meaning that the normal vector is pointing outwards. So yeah, we've verified that this normal vector is a normal vector that's pointing outwards. Okay, so yeah, things are great. Now that we know what our normal vector is, see, let me write out the entire formula. Should be the double integral along the surface, the force field dotted with the normal vector, du dv. Okay, so we know what our normal vector is. Let me just move it down. force vector is x, y, z, z. So you have a problem. This force vector isn't written in terms of r and theta, but we can only evaluate this integral with respect to those two variables. So what we're gonna do is we're gonna rewrite our surface, or just bring it down like this. We can rewrite our force field in terms of these. So remember how this is x, that is y, and that is z. So what we can do is we can just substitute these values in here with these. So x becomes r cos theta, x, y, z is just the product of these three. So r squared cos theta sine theta, and z is just 9 minus r. So now let's dot these two. So r cos theta times r cos theta is r squared cos squared theta. And r sine theta times this function right here is r cubed sine squared theta cos theta. And if we dot the z components, we get 9z, or 9r minus r squared. All right, so we know what f dot n is. That said, we can plug it back into our flux integral. So that gives us, okay, I'm not going to write it all over again. I'm just going to do that. So the two variables we're integrating with respect to are d theta and dr. Now you could also integrate with respect to r and then d theta, but integrating with respect to d theta would be more convenient. And the reason for that being that a lot of terms tend to cancel out if you're integrating with respect to an angle that goes all the way around. So okay, I didn't write the limits for this parameterization, but the limits are for theta. The limits for theta are limit for theta is 0 to 2 pi. The reason for that being that the surface goes one full revolution around about the x and y axes, and r goes from 0 to 9 because the innermost distance on the surface is at the top, and it's at a distance 0. The farthermost distance of the surface is equal to 9. Yeah, so like the farthest the surface goes from the origin is 9 units, and the closest it gets to the origin is 0. So that's why we're going to say r goes from 0 to 9. So yeah, these are our limits, and those are also going to work out to be our integration limits. So yeah, I'll just quickly show you guys what happens if we integrate with respect to theta first. So theta goes from 0 to 2 pi, and r goes from 0 to 9. So what happens to this function is, okay, well, I'm not going to integrate cos squared theta because I have an integration table. So yeah, so like if you guys have an integral table, you just look up the formula for cos squared theta. It's just 1 over 2 theta plus sine 2 theta over 4. And obviously you're going to go from 2 pi to 0. And then the middle function, well, from inspection, you know that the cosine theta probably comes from the chain rule if you're differentiating the function sine cubed theta divided by 3. So if you differentiate the function sine cubed theta over 3, the 3 goes away from the cubic power of your sine term, and a cos theta term appears because of the chain rule. So yeah, just by inspection, you know that the integral of sine squared theta cos theta should equal to sine cubed theta divided by 3. So because we're only integrating with respect to theta, the r cubed term stays the same. So yeah. And then 9r minus r squared can be treated as a constant. We can put them inside brackets just to make things simple. We can multiply that by theta. And obviously theta goes from 0 to 2 pi once again. And can't forget, we still have another variable to integrate with respect to. Okay, so a lot of things cancel out. Did I do this right? All right, I just realized it's a tiny error here. This is only xy. Should multiply it by, forgot to multiply it by z. So let's just throw in the z term right here. Alrighty. Let me fix this real quick. All right. Okay, now we have our z term back. But it doesn't really matter because this cancels out. And the reason for that being is that if you evaluate sine cubed theta at 2 theta and subtract it by sine cubed theta evaluated at 0, like sine, remember how the sine function kind of looks like this? Like you're kind of just, like in this case, you're kind of just evaluating the sine theta function at the same points, but like on different periods, and then subtracting the two. Like you're just subtracting the same number by the same number, so that becomes 0. Okay, and then here we know that sine 2 times 2 theta, or sine 2 times 2 pi minus sine 0 is also 0 because both of these values equal to 0. So whenever sine, like sine n pi is essentially equal to 0. So like any multiple of pi within a sine is equal to 0. And that just comes from how the sine function looks like. So that's a 0. That goes to 0. Okay, now we can evaluate the remainder of our thetas at 2 pi. So this evaluated at 2 pi gives us pi r squared. This evaluated at 2 pi gives us 2 pi 9r minus r squared. So I got to integrate with respect to r. And now if we integrate with respect to r, this term becomes pi r cubed divided by 3. This term becomes, okay, let's keep the 2 pi out, 9 times r squared divided by 2 minus r cubed divided by 3. And obviously we're still going from 0 to 9. And so, yeah, what this works out to be, so like this just happens to work out to be 15 to 7. So yeah, that's an answer to the first example right here. Right, I have another example that I wanted to go over. It's a scalar surface integral. It's the other type of surface integral that I wanted to go over in this video. Okay, so the parameterization is going to be exactly the same because it's the same surface. R is equal to r cos theta, r sine theta, and 9 minus r. So yeah, and r goes from 0 to 9, and theta goes from 0 to 2 pi. And the integral that we're going to set up will look something like this. F is just 1 because we're only looking for the surface area of this cone. And dA is the formula that we're going to use to find dA. dA is the normal, or the length of the normal, multiplied by two variables in question. So we know from before that the normal is r cos theta, r sine theta, r, I think. Let me double check. Okay, it's r cos theta, r sine theta, r. So spot on. Photographic memory. Okay, so the length of this vector would just be r squared cos squared theta plus r squared sine squared theta plus r squared, all underneath the square root, multiplied by the integrand. And because there is a cos squared and sine squared theta term inside the radical, we should probably simplify, and then, yeah, we should probably simplify this. So r squared, so this can simplify to r squared cos squared theta plus sine squared theta plus r squared. And this just works out to be square root of 2 multiplied by r dr d theta. Yeah. Okay, now we can start working on our surface integral. Theta goes from 0 to 2 pi, r goes from 0 to 9. And yeah, there aren't any theta terms, so we can just plug it in like this. dr goes from 0 to 9. Take out the constants. Integrate. And what we have left is square root of 2 pi, divided by 2, multiplied by 81, which works out to be 360. Let's say units squared, if we like. Now, what I'm going to do to just confirm whether this question is right, I'm going to use the theorem of Pappus. So basically I'm just going to revolve a line, a straight line like this, about the z-axis. So this line is going to have its length. Okay, so like this length is just 9 units. That length is 9 units. The length of this line should be 9 squared plus 9 squared under square root. That's just square root of 2 times 81. Okay? And then the path that the centroid of this line is going to travel, it's going to have a radius of 9 divided by 2, because the centroid of this line is in the middle. So, okay, so the radius of the path of travel is going to be 9 over 2. And then we know the circumference is 2 pi r. So 2 pi times 9 over 2. And then now we can work out the surface area. It's equal to this path multiplied by the length of this line. Multiplying the two, we get 9 pi times 81 times the square root of 2. It's not the same thing. Okay. I'll have to cut the video. Okay, so I just realized that this is wrong. This is actually equal to the square root of 126 or 162, meaning that this should be equal to the square root of 162 times, or no, it would be 9 pi multiplied by the square root of 162, which is equal to 360, the same answer we got up there. So we did our surface integration right. Okay, that concludes today's video. And as a summary, just went over a summary of this video. There are two types of surface integrals. The first one being a flux integral, a flux surface integral, and the second one being a scalar surface integral. So you have to use the flux integral formula if your F field is a vector field. So you know whether your F field has a, whether it's a vector if it has a arrow on the top and it has an x, y, and z component. And you're working with this. If you have to work with a scalar formula, if there's no if there's no arrow on top of your function, so that means you're working with a scalar function, and it doesn't have an x, y, and z component. We went over two examples. The first one being a flux integral where we had a surface and a vector field, and we just evaluated a flux integral for these two things. And in the second example, we calculated the surface area of this surface right here and verified it using the theorem of Pappus. So yeah, that concludes today's video. See you guys in the next one.